Hi, this is my video number 9. Okay, so in this video I'll talk on the again solution of non-homogeneous random integral equation by successive approximation, particularly the Neumann series. Yeah. Solution of non-homogeneous random integral equation we solve using successive approximation. Also known as the iterative method. Particularly a Neumann series. Okay, so we consider the non-homogeneous random integral equation ux fx plus lambda integrate ab kxt ut dt. Okay, we are going to solve this equation. Now let's u naught x equal to fx, okay, as a zero approximation, to the required solution. And solution in this case we are looking for is ux. Okay, then the n order and n plus 1 order related by n, then the n and n minus 1 order of approximation, order of ux, related to u and x as fx equal to lambda a to b kxt u n minus 1 t dt. Okay, then the iterated kernel, as we have seen in the previous videos, iterated kernel is defined as k1 xt kxt and kn xt as integrate a to b k xs kn minus 1 st ds. Now if you substitute n equal to 1 into that equation, so let's give a name. So let's call this equation 1, let's call this equation 2. Okay, let's call this equation 3. So if we choose n equal to 1 in 2, so we have u1x is equal to fx plus lambda integrate a to b, so we have kxt, here is u naught t dt, but we have u naught t is equal to ft by our zero approximation. U naught t is ft. Okay, then if we substitute into that equation, we have u1x is fx plus lambda a to b kxt ft dt. Okay, then for the second order approximation, we take n equal to 2. In 2 we have here we have u2 x equal to fx plus lambda a to b k. I can use that as xs u1 s dt. Okay, then we need to substitute those u1, and so if you substitute this u1, this is u1 x, this is u1 s, you just change s with x with s, yeah. So now we're going to have fx plus lambda a to b kxs. Okay, u1 s is given as fs plus lambda integrate a to b k, so x with f, so st ft dt, right, dt, yeah, dt, and I think we should have ds, yeah, ds. Is that correct? So we have, this is ft here, or this one should be ds, so ds. Okay, then if we simplify this or open up this bracket, we have fx plus, that's a lambda integrate a to b kxs fs ds plus, so we have lambda squared integrate a to b kxs kst dt ds. So of course we can change the order of integration. Yeah, you can change the order of integration. I think I missed one integration here. Yep, this one should be a to b. Okay, and then if we change the order of integration, what we have, change order of integration. So what we have, u2x from here, right, u2x fx, and we need to change the order of integration for this. So instead of dt, we integrate the s first. All right, rearrange those things. So we have so u2x is given as fx plus lambda integrate a to b k xt ft dt. Doesn't matter if, because t here is this just a dummy variable, so you can use s, you can use t. All right, plus we have a lambda squared integrate a to b ft, then integrate a to b k xs kst ds dt. Okay, that. Now we use the relation that we obtained earlier, which is the iterated kernel here. Okay, so using 3, so what we have, we just change k is actually k1, and then we use the iterated kernel. So we have u to x equal to, we have fx plus, so lambda integrate a to b. Here we have k is a k1, yeah, from the iterated kernel. We have k equal to k1. So we have k1 xt ft dt plus, you have lambda squared integrate a to b. We have ft here, and this is you can change k is equal to k1, so that gives you k2. Alright, so now we have k2 st ft dt. Okay, one of these as a k1, and whole things here is k2, so that's why we have k2. So we have k2 f dt. And you can write this in terms of series if you want. You can write this as a, or you can write that as a u to x. This is equal to fx plus, so we can see this is lambda squared k1 k2, the rest are the same. So we sum m equal to 1 to n lambda m integrate a to b km xt ft dt. This is 2. So if you proceed this, keep on substituting the using the iterated kernel, and as well as we use the definition of n terms here for u, yeah, we can find u1, we have found that, u2, we have found u2, and then we can find u3, u4, and so on up to un. If you proceed this, you have the n terms is given as unx fx plus summation those things m equal to 1 to n lambda m integrate a to b km xt ft dt. Then if you take the limit n goes to infinity, yeah, take the limit n goes to infinity, so we obtain what we call as a Neumann series. So that's why we call it as a Neumann series solution to the non-homogeneous Freedom integral equation. So those Neumann series is given as ux is, actually we take a limit n goes to infinity unx. This equal to fx, we take a limit fx, I still give you fx plus sum, we take n goes to infinity, so you have m equal to 1 to infinity lambda m integrate a to b km xt ft dt. So this is the solution to the non-homogeneous Freedom integral equation. All right. So if this is the solution, then we can determine, or we can identify what is the kernel or the reciprocal kernel or the resolvent kernel yeah, for the solution. Okay, so if we change the order of integration between integration and the summation here in this case, yeah, now we need to determine, this is the solution. Now we need to determine, I put it here, we need to determine the resolvent kernel. Okay, or reciprocal kernel, R xt lambda. Okay, so if we change the order of integration between summation and integral, yeah, change the order of integration and summation, so we have ux is equal to fx plus, just take out one lambda, integrate from a to b, then we have summation m from 1 to infinity, lambda m minus 1 km xt ft dt. The integration, okay, so here, there. Right? Then if you compare with the general solution, yeah, the general solution that involve the resolvent kernel. So the solution that involve resolvent kernel, what we have is ux fx plus lambda integrate a to b rx t lambda ft dt. Okay, so we compare with. The purpose is to determine our R here, the reciprocal kernel or the resolvent kernel. So what we have is that R xt lambda, this is equal to that part here, alright, summation of lambda m minus 1 km xt. So the resolvent kernel for the Neumann series is given as that. Now we need to determine the condition of the convergence of the Neumann series, because this is the series, this series solution here. So we need to determine this series converge, and also we need to determine the resolvent kernel that we have is a unique, as well as the solution is unique. So we are going to focus or discuss on the convergence of the series, as well as the uniqueness of the solution and the kernel. Okay, now for the condition of the convergence, condition of the convergence of Neumann series, now from the where is it? So from the this solution, where's the Neumann series? From the Neumann series solution here. Okay, big N goes to infinity, so that one, and we consider only this part here, and we use the Schwarz inequality. So what we have, if we consider the apply the Schwarz inequality to that terms, so we have integrate a to b km xt ft dt squared. Okay, for that terms only, we have this is less than integrate a to b km xt squared dt integrate a to b ft squared dt. Okay, so what we do here is that we apply Schwarz inequality as Schwarz inequality to that form, to that terms. And we can write the norm of ft and norm for ft. Norm for ft, we denote that, let's say, d as a norm of ft. This is that part here, integrate a to b ft squared dt half. Okay, that's the definition of the norm. And then further, if we consider this part here have a limit c2, and also we let the integration of the kernel, all right, integrate a to b the km xt squared dt less than some numbers cm squared, say. Okay, so we use this, the norm for ft, as well as bound for that condition, I mean, or for that that terms, integrate a b km x t squared dt less than some number cm. We use that so into those expression or those inequality. So what we have, the integrate a to b km xt ft dt squared. This is less than or equal to, so this part here is cm squared and this part is d squared. So we have cm squared d squared. And then we apply the again the Schwarz inequality into the iterated kernel. Also we have we apply the Schwarz inequality to the iterated kernel. So we have km xt squared. This is less than. So integrate a to b km minus 1 xs squared ds. Integrate a to b kst squared ds. Okay, and then if you integrate this with respect to t, you integrate this side a to b with respect to t. Okay, and then we need to integrate this side as well with respect to t. So you can put here a to b respect to t. Okay, so what you have, this integral becomes integrate a to b km xt squared dt. This is less than, we have a b squared, yeah, from, so we have b squared. I think from the previous definition we have b, where is it? Let me look for that. I'm gonna find one. Okay, so we have c, this one is c minus 1 squared, so we have c m minus 1 squared. Okay, and for that we can define those as a b squared. So where b squared is equal to those summation, double integration a to b, we have k xt squared dx dt, or dx dt, or dx dt. So you just, if s, you just change with s, so we have ds dt. Okay, from this relation, okay, from that relation and as well as that relation, so we obtain that c m squared less than b 2m minus 2 c m minus 1 squared. And from that we have, because this is cm, if we multiply this by d, so we have d here, so we multiply by d squared, for example, then I also need to multiply this by d squared. So therefore we have d cm squared, which is this, less than that. Okay, so which means this part here less than that. So we have, therefore we have integrate a to b km xt ft dt. This is less than or equal to c squared cm minus 1 squared d squared b 2m minus 2. Okay, so from here it is obvious that if you consider this magnitude of that terms here less than some numbers, you can I think we have squared here. So what we have here, if you remove those, if you square root each both sides, so we have integrate a to b km xt ft dt. This is less than, we have c m minus 1 d squared b m minus 1. Okay, and we have a lambda in front. So in order that this series converge, because we are looking for the condition for the convergence of the Neumann series. You remember that Neumann series we have lambda in front. So which means everything there we have lambda. So what we need now is that this condition, and plus since we have lambda, so I can put that lambda as well there, lambda m minus 1, because we have lambda m minus 1 here, lambda m minus 1. Alright, so I can put it here. So basically we also have lambda m minus 1. So in order to ensure that this series converge, so we need this lambda b, this is less than 1. So if we apply this lambda b less than 1, so what we have is lambda b less than 1, and we know that b square, I've defined somewhere, just let me look at the papers. Where is it? Okay, yeah, b squared is given here. So we have b squared is defined as integrate a to b kxt squared dx dt. So therefore I have lambda less than 1 over b is given here, so we have 1 over integrate a to b kxt squared dx dt to the half, because we have square root there. So this is the condition that to ensure the solution, the Neumann series solution, uniformly converge. Okay, so next we look at the uniqueness of the solution as well as the resolvent kernel. We look at the uniqueness of the solution U and the uniqueness of the resolvent kernel. Let me just write x t lambda. Yeah, first we look at the uniqueness of U. So let's the non-homogeneous Freedom integral equation has two solutions. Let's say u1x and u2x. So therefore, since u1, u2 are the solution to the non-homogeneous Freedom integral equation, so I can write u1 satisfy the Freedom integral equation. So you will have u1 x is equal to fx plus lambda integrate ab kxt u1t dt, and also we have u2x, this is fx plus lambda integrate ab kxt u2t dt. Okay, then if we subtract u1 u2 from u1, so we have subtract u2 from u1, so you have u2, so you have u1x minus u2x, this is equal to fx give you 0, that will give you lambda integrate a to b, and then you can factor out u1 and u2. So what left is kxt u1t minus u2t dt. So I can define this function as phi t, and therefore this function as a phi x. Just give a definition. We just define that. So we have here that phi x is equal to lambda a to b kxt phi t dt. So if you recognize, this is the homogeneous Fredholm integral equation. Yeah, homogeneous Fredholm integral equation. Now, if you apply this source inequality, apply source inequality what we have that phi x squared, this is less than lambda squared integrate a to b kxt dt integrate a to b phi t squared dt. Then we integrate this with respect to x from a to b, so means we integrate the left side as well as the right side. So integrate this with respect to x, a to b dx, so we can integrate this a to b with respect to x. We give it that. Okay, so I think because here we have a function x here, so we integrate on k. Not here, we integrate here. Integrate a to b dx. Then using the previous relation that we have defined earlier, b, this is given as b, so we have this is b. Alright, this is which is squared here. So this is our b squared. So what left is we have integrate a to b phi x squared dx. This is less than we have lambda squared b squared, then integrate a to b phi t dt. dx here phi x. Okay, now this is because we change the order of integration. Yeah, and then from there you can rearrange this. That give you 1 minus lambda squared b squared integrate a to b phi x squared dx, that less than equal to 0. And we know that lambda b is less than 1, that less than 1. So 1 minus something less than 1 is less than 1. So the whole thing here, this is less than 1. So what left is this part must be 0 in order to get the equality. So therefore we have integrate a to b phi x squared dx, this due to 0. So from there, because of the definition that phi we define as u1 minus u2, so what we have is that phi x squared, that gives you 0, which is means u1x minus u2x squared, this is 0, and from there we have u1x is equal to u2x. So therefore the solution is unique. Yeah, because from the beginning we assume that the Fredholm integral equation have two solutions, and later we show that those two solutions are equal. So therefore the solutions are unique. Okay, now we can do the same for the to show the uniqueness of the kernel, uniqueness of the resolvent kernel. Okay, for the resolvent kernel for R x t lambda. Okay, so okay. So let's say the equation, our Freedom integral equation. Our Freedom integral equation is ux equal to fx plus lambda integrate a to b kxt ut dt. And the solution is given as ux equal to fx plus lambda a to b r xt lambda ut dt. Okay, so let those things has the solution given as that. Now let's say this solution has two resolvent kernel R. So let R1 x t lambda and R2 x t lambda be two resolvent kernel with lambda equal to lambda naught. So which means so if you substitute that, because and remember that the solution is unique. So for R1 we have U1, for R2 we have U2, and since they are unique, so U1 equal to U2. So what we have, that terms with R1 equal to that term with R2. So what we have is and R and F left hand side, right hand side cancel out. So what we have now is that lambda naught integrate a to b R1 xt lambda. So ft this is f, ft dt equal to we have lambda naught a to b R2 xt lambda dt, ft dt. Okay, and then you can again rearrange this. So what we have, rearrange those, what we have is that integrate a to b R1 xt lambda naught minus R2 xt lambda naught ft dt. This is equal to 0. Then we can define this. Let's define that as R, f xt lambda naught. So we need to show that f is 0, so therefore R1 equal to R2. So for this equation, if we define R1 minus R2 as f, so what we have now, just rewrite those. A to b f xt lambda naught ft dt, that's equal to 0. Then we can define an arbitrary, because f is any arbitrary function, so then we can define ft as f xt lambda naught, as this is as a conjugate to the to f, conjugate to f, conjugate to to f. So we can do this because f is arbitrary function. So if we take ft as a conjugate of capital F, so then we have integrate a to b, because this is f times conjugate of f, that give you f xt lambda naught squared dt, that give you 0. And from this we can have f xt lambda naught, this is 0, and therefore since our f we define as r1 minus r2 and they are 0, that will give you r1 x t lambda naught equal to r2 x t lambda naught. So from here what we show is that the resolvent kernel is unique. Yeah, the resolvent kernel is unique. We also have shown that the solution, the Neumann series solution to the homogeneous, non-homogeneous Freedom integral equation is unique. And at the beginning, I've shown that how we can apply the iterative method to obtain the Neumann series solution to the non-homogeneous Freedom integral equation. Okay, I think after this we are looking at the some example. We discuss some example in the next video. So for the time for this video, I think I'll stop here. Then see you in the next video. Bye.